Ampere's circuital law we consider a conductor which extends from minus infinity to plus infinity. The current in the conductor is I. We consider a closed path of radius rho around the current carrying conductor. So we consider a closed circular path of radius rho around this current carrying conductor. dl represents the differential length vector along this closed circular path. So let us consider this point P, and let us calculate the magnetic field intensity at this particular point. The magnetic field intensity at point P is given by equation number 19. The magnetic field intensity at the point under observation will be equal to I by 2 pi rho into A phi. Then we consider the differential length vector along the closed circular path, and we know that the differential length vector along the closed circular path is equal to rho d phi A phi. We calculate the scalar product of these two vectors. So let us calculate h dot dl. As you know that these two vectors are in the same direction, and a phi dot a phi dot a phi will be equal to 1. So as a phi dot a phi will be equal to 1, definitely h dot dl will be equal to I by 2 pi into d phi. So let us integrate the magnetic field intensity around this closed path. So the integral of the magnetic field intensity around the closed path will be equal to I by 2 pi, the integration from 0 to 2 pi of d phi. So we integrate d phi. The integration of d phi is phi, and if we put the limits, then we get 2 pi. So the integration of the magnetic field intensity around the closed path will be equal to I by 2 pi into 2 pi. So the integral of the magnetic field intensity around the closed path will be equal to the current in the conductor. And you see, as the conductor is enclosed by the closed path, if we consider this diagram, you see the entire conductor in this diagram is located inside the closed path. As the entire conductor is located inside the closed path, so we can say that the current in the conductor is located inside the closed path as well. So if we look at equation number 20, we can say that the integral of the magnetic field intensity around the closed path will be equal to the current enclosed by the closed path, and this law is known as Ampere's Circuital law. So let us define Ampere's Circuital law in light of equation number 5.20. Ampere's Circuital law states that the integral of the magnetic field intensity around a closed imaginary path is equal to the current enclosed by the closed path. So this is Ampere's Circuital law. This is a very important law. There are so many applications of this law. We can consider the current carrying conductor, which extends from minus infinity to plus infinity, and we can find out the magnetic field intensity which is caused by this conductor with the help of Ampere's Circuital law. We can consider a coaxial cable, and we can find out the magnetic field intensity at different locations of the coaxial cable with the help of this Ampere's Circuital law. Similarly, we can consider an infinite sheet of current, and we can calculate the magnetic field intensity at any point due to the current in the infinite sheet, and the magnetic field intensity at any point which is caused by the current in the infinite sheet is equal to 1 over 2, and then we have K cross AN. So K is the surface current density. K is the surface current density, and the surface current density is the current per unit width of the sheet. If you divide the total current of the sheet by the width of the sheet, you guys will get K. So the current per unit width of the sheet is known as surface current density, and we consider this surface current density is a vector quantity. You see, the direction of this surface current density is the direction of the current. So whatever may be the direction of the current in the sheet, that will be the direction of this K. And AN is a unit vector which is normal to the sheet. So we use this particular equation to find out the magnetic field intensity at any point, and this magnetic field intensity is caused by the current in the infinite sheet. Well, we have already discussed the second equation of Maxwell in this particular chapter. So here is the second equation of Maxwell. The divergence of the magnetic flux density is always equal to 0. So the divergence of the magnetic flux density is always equal to 0, and this equation is known as the second equation of Maxwell. The divergence of the magnetic flux density is 0. This is the second equation of Maxwell, and we derived this second equation in chapter number 8, in the beginning of chapter number 8. As far as the first equation of Maxwell is concerned, we derived the first equation of Maxwell in chapter number 3, which says that the divergence of the electric flux density is equal to rho V, where rho V is the volume charge density. And what is the volume charge density? Volume charge density is the charge per unit volume. So this is the first equation of Maxwell, which says that the divergence of the electric flux density is always equal to rho V, and rho V is known as the volume charge density, which is the charge per unit volume. So let us talk about the third equation of Maxwell, Maxwell's third equation. And for the third equation of Maxwell, we consider a current carrying conductor. We consider a current carrying conductor. The current in the conductor is I. The current in the conductor is represented by I, and the cross-sectional area of the conductor is represented by S. We know that current density is the current per unit area. So the current density will be equal to the current per unit area excuse me. The current in this conductor is I, and the cross-sectional area of the conductor is S. So the current density of this conductor is equal to I by S. So this is the conduction current density, which is basically the current per unit area. The current in this conductor is I, and the cross-sectional area of this conductor is S. This is how we calculate the current density. So let us assume that this conductor is along z axis. So if this conductor is along z axis, then the current in this conductor will be along z axis, and we can consider the current density as a unit, the current density as a vector quantity. So the current density will be in the direction of the current, and if the conductor is along z axis, then the current will be in the direction of the unit vector Az. Similarly, if we consider the unit vector which is normal to the cross-sectional area of this conductor, the unit vector which is normal to the cross-sectional area of this conductor is Az as well. So we can represent the cross-sectional area of this conductor as a vector quantity, and the cross-sectional area of this conductor as a vector quantity will be equal to S Az, the unit vector which is normal to the unit vector which is normal to the cross-sectional area of this conductor is Az as well. So S Az is the cross-sectional area of this conductor in the form of a vector quantity. So we consider the current density in the form of a vector quantity. The current density will be in the direction of the current, and the current is in the direction of the unit vector Az. Similarly, the cross-sectional area of this conductor is in the form of the unit vector Az as well. Az is the unit vector which is normal to the cross-sectional area of this particular conductor. So if we look at this particular equation, you see, we can find out the current from this equation, and the current from this equation will be equal to Js. So you guys can find out the current in the conductor in terms of the current density and the cross-sectional area of the conductor. So as these two vectors are in the same direction, the current density and the cross-sectional area are in the same direction, so Js will be equal to J dot S. Why? Because in this particular case, the current density and the cross-sectional area of this conductor are in the same direction, and J dot S will be equal to Js. We can consider a very small portion of the cross-sectional area, which is represented by ds, and we assume that the current in the small portion of the cross-sectional area of this conductor is di. So we can calculate the current density with the help of this equation as well. The current di by ds will be equal to the current density. So we can calculate the current density with the help of di by ds as well. Now we can represent a ds in the form of a vector quantity. The unit vector, which is normal to the small portion of the cross-sectional area of this current carrying conductor, is Az. So we can calculate the differential current from this particular equation. The differential current will be equal to J into ds. So we can calculate the differential current from this particular equation, and the differential current will be equal to Jds. So as J and ds are in the same direction, so we can replace Jds by this scalar product. J dot ds will be equal to Jds, because J and ds are in the same direction. So this is the differential current, and this differential current will be in the small portion of the cross-sectional area of the conductor. If you want to find out the total current, we need to integrate this particular equation, and the integration of this particular equation will give you the total current in the conductor. So the current in the conductor will be equal to the integral of J dot ds. Now we apply Ampere Circuital law. And for the application of Ampere Circuital law, we consider a closed path around this current carrying conductor. We consider a closed path around this current carrying conductor, and we apply Ampere Circuital law. And Ampere Circuital law states that the integration of the magnetic field intensity around the closed path will be equal to the current enclosed by the closed path. And the current enclosed by the closed path is the current in the conductor, and you see the current in the conductor is given by this equation. The integration of J dot ds gives you the current in this particular conductor. So we consider this particular equation. The closed path integration of the magnetic field intensity will be equal to the integration of J dot ds. In other words, the integral of the magnetic field intensity around a closed imaginary path will be equal to the current enclosed by the closed path, and the current enclosed by the closed path is the integral of J dot ds. We consider the left hand side of this particular equation, and we apply the Stokes theorem. According to the Stokes theorem, the closed path integration of the magnetic field intensity can be calculated with the help of this particular integration, and we have the integration of del cross H dot ds on the right hand side. What is del cross H? Del cross H is known as the curl of the magnetic field intensity. How do we calculate the curl of magnetic field intensity in rectangular coordinate system, cylindrical coordinate system, and spherical coordinate system? We will explain these equations later on. So we replace this closed path. We replace this closed path integration of the magnetic field intensity by the integration of del cross H dot ds. So we consider the second equation of this page, and we replace the closed path integration of the magnetic field intensity by the integration of del cross H dot ds, which is equal to the integration of J dot ds. And if we consider the left hand side with the right hand side, which says that the curl of the magnetic field intensity will be equal to J. So the curl of the magnetic field intensity is equal to J. This equation is known as the third equation of Maxwell. Well, this equation is incorrect, but anyhow, we consider this equation the third equation of Maxwell, and we will correct this equation later on. How do we calculate the curl of the magnetic field intensity in rectangular coordinate system? So we can calculate the curl of the magnetic field intensity in rectangular coordinate system with the help of the determinant, which is on the right hand side. In the first row of this determinant, we consider the three unit vectors. There is the unit vector ax, the unit vector ay, and the unit vector az. In the second row of this determinant, we consider curly by curly x, curly by curly y, and curly by curly z. In the third row of this determinant, we consider the x component of the magnetic field intensity, that is hx, the y component of the magnetic field intensity, that is hy, and the z component of the magnetic field intensity, that is hz. So we calculate the curl of the magnetic field intensity in the rectangular coordinate system with the help of the determinant, which is on the right hand side. If the magnetic field intensity is in the cylindrical coordinate system, then we calculate the curl of the magnetic field intensity with the help of this particular determinant. So if the magnetic field intensity is in the cylindrical coordinate system, the curl of the magnetic field intensity will be equal to 1 by rho. Then we have a rho, rho a pi, and az. And in the second row, we have curly by curly rho, curly by curly phi, and curly by curly z. In the third row, we have h rho, which is the rho component of the magnetic field intensity, rho h phi, and then we have hz. So we use this determinant to find out the curl of the magnetic field intensity in the cylindrical coordinate system. If the magnetic field intensity is in the spherical coordinate system, then we use this particular determinant to find out the curl of the magnetic field intensity. So the curl of the magnetic field intensity will be equal to 1 over r square sine theta. We have a r, r a theta, r sine theta a phi. In the second row, we have curly by curly r, curly by curly theta, and curly by curly phi. In the third row, we have HR, R H theta, and R sine theta H phi. So we use these determinants to find out the curl of the magnetic field intensity in the rectangular coordinate system, cylindrical coordinate system, and spherical coordinate system. We shall do the numerical questions of this chapter later on. Thank you so much.